Hello everyone and welcome. This is Hugh here at Loxone and I'm here today with another one of our focus series videos. In today's particular topic, we are going to be looking at heating. Now, when we look at a lot of different heating configs in Loxone, we quite often look at wet heating systems and wet heating scenarios, but of course there are many different occasions where you'll be doing electric heating. Now, that could be in flats that have either panel heaters or they have storage heaters. It could be in electric underfloor heating for bathrooms. There's a lot of different scenarios where electric heating makes sense and is used. Now, of course, we can do these perfectly in Loxone. So this webinar is really just to show you the best possible ways of doing it. And so what we're going to be doing is we're going to be looking at a particular scenario, which is this: electric heaters in a flat. So we have a fairly typical UK flat that has an open plan living room, kitchen and dining room. It's got 2 bedrooms and it's got a bathroom. And in each of these rooms, we have infrared panel heaters. So in the bathroom and the 2 bedrooms, there is 1 infrared panel heater in each room. And in the open plan living room, kitchen and diner, we've got 3 infrared heaters. And we're going to look at how to intelligently and efficiently manage these using Loxone. So if I just move over to the config file that I have pre-prepared, as you can see, I've just got a blank config file to start with. Now, the first thing I've done is I have created these rooms. And really importantly, you'll see that I've filled out room sizes. Room sizes are quite important for heating config within Loxone because they are used for some of the internal logic of working out heating up and cooling down phases. So that's the first thing. The second thing is how I control this electric heating source. Now, essentially, if you've got electric heating, it's digital, on or off. It doesn't vary. You can't vary it with an analog signal on and off. So we need relays to control them. Now, of course, if you're doing things like like electric underfloor heating, you may have relays from a mini server, you may have relays from a relay extension, you may go through coupling relays or contactors if they're very high loads. What I've done is I have pre-created myself an airbase extension, and all of my IR panels in my example, apart from the bathroom, are going to be running off of smart sockets. The reason being is that a smart socket nicely has a temperature reading, a temperature sensor built in as well. So it gives us a fairly simple, fairly effective way of controlling these different heat sources without having to add lots and lots of extra hardware that we may not need. The one exception is the bathroom, because I doubt I would get away with sticking a smart socket in a bathroom. So I have assigned a relay for the bathroom heater, and I've put a touch air in the bathroom for my temperature sensor. So whenever we do heating or cooling with Loxone, the thing that we need in each room that we're going to be managing is a temperature sensor. And so, as I said, smart socket's got one built in, and I've got a touch air in the bathroom. And so what I need to do to get started is I need to, first of all, make sure that I've got all of my pages created for each of my rooms. So I'm just going to have a page for each of the room types I've got. So kitchen, dining, and living. And I'm going to put the default room as that as well. And that ensures that anything that I dump onto that page will be added to that room by default. I've got the bathroom, which we can see there. I've got bedroom 1, bedroom 1, and finally bedroom 2. So I've got all of my pages pre-created. Now, with heating control for electric heating sources with Loxone, just as we normally would, we're going to use an intelligent room controller. There's no difference here. We still use an intelligent room controller in each room, and only 1 per room. And on that intelligent room controller, we're going to tie the temperature reading into the inputs, onto the TI inputs, and then on the outputs, we need to put our heating source. So normally, if we were doing wet heating, we would usually end up with intelligent temperature controllers and climate controllers as well, because we would need to manage the source separately to the individual zones. Because on a wet heating system, the boiler is the source, but it is providing heat to multiple zones. Whereas what we have here with electric heaters is no one single source. Every room is its own source of heating or cooling. So we don't really need climate controllers or intelligent temperature controllers for what we want to do here. We could just get away with the intelligent room controller, and that's exactly what we're going to do. So instead of assigning a climate controller to it, I am just going to simply use the QH output of the intelligent room controller. QH output is the heating output. Now, the really, really important thing to bear in mind with our intelligent room controller is that the outputs for heating and cooling by default are analog. They give a 0 to 10 value. And the reason for this is that our valve actuators are also analog. We can set a particular level that they need to go to. But of course, our relay that we want to control, so in this case, our relay for the bathroom heater, is digital. Now, what's going to happen if I stick a digital output, so this relay, onto something that gives me an analog value, is as soon as this value goes 1 or above, it's going to turn this bathroom heater on, which doesn't make sense, because that means that that room is likely going to massively overheat because of the speed at which this heater will likely be able to heat that room up, and the room controller will have trouble learning, and it's also going to be inefficient. So what we need to do is we need to have a way that we are effectively turning this heater on and off based on the level of demand on this output. And so we have a few ways that we can do that. The first way is you do have the option to enable PWM outputs. And what that means is that turns the outputs from being analog into being digital instead, but using pulse width modulation. So they will actually be turning on and off over a period of time to modulate a digital source. Now, one thing to bear in mind with PWM, if I hover over, it should even tell me this. There we go. PWM signal is output. If the cycling period is relatively short, for this reason, it is not suitable for the direct switching of large loads, e.g. infrared heaters. So it's straight away telling us that PWM is not suitable for infrared heaters. And the reason for that is that the cycle time on the PWM may be relatively short. It may be over a period of a few minutes. Now, if we're switching the relay on, let's say, a mini server or a smart socket, or even a third-party contact or a coupling relay, switching it over several times every few minutes, it's going to degrade the lifespan of that relay, and therefore it's eventually going to fail sooner rather than later. Now, one thing we could do to get around that is we do actually have a parameter for TPWM, which is the PWM interval. Now, by default, it's 0, which means that it works out itself. If you wanted, you could set that to a much higher PWM interval, like 60 minutes, to try and get around this cycling time issue. However, that still wouldn't be my preferred way of doing it. I would actually prefer to keep this output as analog and actually, based on the value here, decide whether this heater should be on. Now, there are a few ways that I can do that. I could, first of all, use something like a status block. So I could have that output into a status block, and in my status block, I could say that if AI1 was greater than or equal to 5, that it would output a value. So then this value here has to be at least 5 before it will turn the output on. So that would be one way of doing it. I could use something like a threshold switch. And with a threshold switch, I could say that it has to hit a value of 5 before it goes on. And then it has to get back down to, let's say, 3 before it goes back off again. And so that would work as well. And there are various other analog comparisons, different function blocks I could use. I could use a comparison block and do greater or equal or just greater than. I could use various other analog blocks like min-max limiters. So there's several different ways that I could do it. My preferred way to keep it nice and simple, and actually it's a block that we've seen on these webinars before, would be a two-position controller. Because if you remember, a two-position controller controls an output based on hysteresis. And so using the two-position controller, we could say that the target value is 5 and that the hysteresis is 2. And what that means by default on the two-position controller is that if we, let's say QH was on 0, it would turn the output on until QH hit 7, and then it would turn the output off until QH then went to 3. Now that's the wrong way around. We need that the other way around. So what we could do is we could then invert this output. And what that means is that any value from 7 through to 10 on QH, so a high demand, will turn this output on, and then that output will stay on until QH drops to 3 or lower. And that then very, very nicely controls our level of demand. And if I show you that in simulation, you can see at the moment QH is giving a value of 10, which means that this bathroom heater is on. And this will now need to drop a value of 3 before the bathroom heater turns off. And then it will have to get back up to a value of 7 before it turns back on again. And that gives us that very, very nice dead band that panel heater can sit in, because a panel heater is going to be very, very quick to heat up and cool down a space. And essentially, that's what I'd need in every room. So in every room, I would put myself an intelligent room controller. I would put in the temperature reading. So this is bedroom 1. So here we have bedroom 1. So our relay, as you can see, by default puts it on HC. So we need to remember to put it on the right output QH, and our temperature reading. And again, we first need a two-position controller. And that two-position controller, in fact, wants to go to QH and the output to the relay. And then two-position controller, target value of 5, hysteresis of 2. And that is what we could do in every single room of the house. So another intelligent room controller in bedroom 2. Bedroom 2, temperature there, relay dragged out, but has to go through a two-position controller first. Again, onto QH. And then the big difference comes with the kitchen, dining, living room. So this is an open plan area with 3 different panel heaters. Now, just because it has 3 different heaters does not mean that it needs 3 intelligent room controllers. If it's an open plan space, it should only have 1 intelligent room controller, and all of those panel heaters should be controlled as one to control the overall heat in the room. So QH, and then again, a two-position controller tied to QH. We would then have our relays all on the two-position controller output. So every one of those 3 relays would all go to QH. And then the other thing is we've obviously got 3 different temperature readings for this room as well. So in this room, we have 1, 2, and 3 temperature readings. Now, the options we have here is, generally speaking, you only want to pick 1 temperature reading to use within a room. So generally speaking, if it's a large open plan area, go for a midpoint in the room and use that as your temperature reading, because your kitchen's probably going to be a little bit warmer, your living room or dining room may be a little bit cooler. Hit a good midpoint and heat the whole room up to that midpoint. You could, of course, average them if you wanted to. Now, a really important thing to note for config and for Loxone is you cannot do this, because if you do that, that is not averaging them. The default function for an input on any function block is automatically ORed. So if I was to do that, it would pick that temperature or that temperature or that temperature. It wouldn't use all 3. So if you did want to average them, then you need to put them through an average function block first. So an average function block allows you to average up to 4 different inputs. And so they would go in there first, and then that output would be what goes into our temperature input there. And that would be the kitchen, dining, living room done. And that is essentially the simplest and most efficient way to do electric heaters within Loxone. No climate controller needed, no intelligent temperature controller needed, just the room controller with the output on, with a bit of logic that dictates when that output should turn on or off based on the analog value that's outputted, and our temperature reading on the input side. And as I said, really, really important to set room sizes. And these room sizes are measured in square meters because it's used for some of the internal logic. The only extra thing you may have to consider in something like this, which is essentially an infrared panel array, infrared panels have a habit, when there's a lot of them, of doing things like tripping MCBs and tripping RCDs. So what you could do, if that was a problem, is instead of having to up anything in the fuse board, you could actually just tie in something like switch on delays. So you could have 3 separate switch on delays into these relays first, each with a different delay duration, so that you're starting them up a second after each other, if that was a problem. However, in this flat, that wouldn't be a problem with 3 panel heaters in one room. And there we have it. Electric heating solved with Loxone. And if I'm in simulation mode, the really, really great thing about simulation mode that you can see is this panel heater is already on because the room is currently reading 0 degrees. In simulation, I have the power to click this and to actually manually change that temperature. So I could change it up to, say, 20 degrees. And comfort is currently set for 22.5. So actually, let's get that closer to 22.5. So let's go for 22 degrees. And you'll see that the output hasn't immediately changed. And that's because the intelligent room controller has a lot of inbuilt logic, part of that being PI controllers, to make sure that it's not constantly flip-flopping between on or off. And what it will do is it will learn over time how to adjust the slope to make sure that it's leveling it out. And so what you'll actually see, if you start whacking those temperatures up and down in simulation, is QH will take a gradual effect. And there'll also be a scanning time as well. So there'll be something like a 60-second scan time in there. But if I do that for the other rooms as well, if I make this one, let's say 22.3, remember to invert the outputs as well. Make this one 23. And then on the average, I'm going to have to set all of them because, of course, it's averaging it. And back to the bathroom. As you can see, it's still at a value of 10, so it still thinks that it needs to heat all the way up. If I now start quite rapidly rising that temperature, and again, giving it a minute pole time in between. So if I whack that up to 24 and we give it another minute, we should start to see this output having an effect. And what it'll likely do, because I'm doing this over a very, very short space of time, it'll likely go between 0 and 10 because it's seeing a very, very rapid change. There we go. So you can see straight away it's gone 0. So because it's seeing such a rapid change, it's going 0, 10, 0, 10. So in simulation, it can be quite hard to actually get this to give you a value other than 0 or 10, because what you'd essentially have to do is leave this running for a realistic amount of time and slowly adjust this temperature up over that period of time. So you'd probably be adjusting it by maybe 0.1 or 0.2 of a degree every 3 or 4 minutes. And there you go. This has already started working. So now we're at 22 degrees. You can see it's outputting a value of 3.2, which is too low for this to turn back on because this has to hit 7 again. So if I started dropping the temperature down, so the room was cooling down, and again, gave that a little bit of time to work out its internal logic and what's happening with that, we should see this figure rising. And so again, it's about a 60-second scan time, so I have to give it that amount of time. May change, it may not. It all depends on what that internal logic is doing for working out the output. But fundamentally, our heating with electric heating is all sorted and doing exactly what we need it to. If I drop that down to 20, so it's had quite a sharp takeoff, again, that output should go fairly high. And there we go, straight away, back to 10. And you can see that it's starting to learn what this room is doing and what the logic of this room is. Excellent. I hope you've enjoyed. That is electric heating in Loxone, and you can use that principle for any electric heating source that you're going to be doing. So whether that be an electric IR panel, whether it's a storage heater, whether it's electric underfloor heating, doesn't really matter. This same logic can apply. Brilliant. I hope you've enjoyed. Please feel free to join me again for our next webinar on a focus topic. Other than that, I'm Hugh from Loxone, and thank you all very much for joining. Goodbye.